Let's go through the steps to solve for the optimal combination of x and y on the east side. We have the following information. Aggregate utility function, u equals x caret 0.5 plus y caret 0.5. Weekly income, R10M. Price of x, R10. Price of y, R20. Step 1. Set up the optimization problem. Maximize u equals x caret 0.5 plus y caret 0.5 subject to the constraint, x plus y equals R10M. Step 2. Set up the Lagrangian function L equals x caret 0.5 plus y caret 0.5 plus lambda, x plus y, R10M. Step 3. Take partial derivatives Lx equals 0.5 x caret minus 0.5 plus lambda equals 0. Equation 1, Ly equals 0.5 y caret minus 0.5 plus lambda equals 0. Equation 2, L equals x plus y, R10M equals 0. Equation 3. Step 4. Solve the system of equations from equation 1, 0.5 x caret minus 0.5 plus lambda equals 0. Solving for x caret minus 0.5 equals dash 2 lambda. Taking the reciprocal, x caret 0.5 equals dash 2 lambda caret minus 1 equals dash 1 or 2 lambda. From equation 2, 0.5 y caret minus 0.5 plus lambda equals 0. Solving for y caret minus 0.5 equals dash 2 lambda. Taking the reciprocal, y caret 0.5 equals dash 2 lambda caret minus 1 equals dash 1 or 2 lambda. Substituting x caret 0.5 and y caret 0.5 in equation 3, dash 1 or 2 lambda plus dash 1, 2 lambda equals R10M. Lambda equals R10M minus 1 equals R10M. M equals dash 1 R10. Step 5. Calculate the optimal values substituting m into the expressions for x caret 0.5 and y caret 0.5. X caret 0.5 equals dash 1 or 2 lambda equals dash 1 or 2 dash 1 or R10 equals R10. 2 equals R5. Y caret 0.5 equals dash 1 or 2 lambda equals dash 1 or 2 dash 1 or R10 equals R10 or 2 equals R10. To find the optimal values for x and y, we square the results. X equals x caret 0.5 caret 2 equals R5 caret 2 equals R25. Y equals y caret 0.5 caret 2 equals R10 caret 2 equals R100. Therefore, the optimal combination of goods x and y that maximizes utility on the east side is x equals R25 and y equals R100. By following these steps, you can solve for the optimal values of x and y using the Lagrange multiplier method. Let's break down the Lagrangian function and the symbols used in the context of this problem. The Lagrangian function is used in optimization problems when we have an objective function to maximize or minimize subject to one or more constraints. The objective function represents the quantity we want to optimize or improve. It could be a measure of utility, profit, cost, efficiency, or any other metric that we aim to maximize or minimize. For example, in the given problem, the objective function on the east side is the aggregate utility function, u equals x caret 0.5 plus y caret 0.5. The goal is to maximize this aggregate utility function, which represents the overall satisfaction or well-being of the customers on the east side. However, optimization problems are not just about maximizing or minimizing the objective function. There can be additional constraints that need to be satisfied in the process. These constraints are restrictions or limitations that we must adhere to. Constraints can include limitations on resources, budget, capacity, or any other condition that needs to be satisfied while optimizing the objective function. In the given problem, the constraint is x plus y equals R10M, representing the total amount of money that can be spent on goods x and y. So, the objective function represents what we want to optimize, and the constraints represent the conditions that we need to satisfy while optimizing. The goal is to find the optimal values of the decision variables, x and y, that maximize or minimize the objective function while respecting the constraints. This process involves using mathematical techniques, such as the Lagrange multiplier method, to find the values that achieve the best possible outcome while satisfying the given conditions. In this case, we want to maximize the utility function u equals x caret 0.5 plus y caret 0.5 while satisfying the constraint x plus y equals R10M. The Lagrangian function is defined as follows: L equals U plus lambda, C, R10M. Where L represents the Lagrangian function. U represents the objective function, which is the aggregate utility. Lambda is the Lagrange multiplier, a parameter introduced to incorporate the constraint into the objective function. C represents the constraint equation, which is x plus y equals R10M in this case. R10M is the weekly income on the east side. By introducing the Lagrange multiplier lambda, we can treat the constraint equation as an additional term in the Lagrangian function. The Lagrange multiplier lambda allows us to simultaneously optimize the objective function and satisfy the constraint. In summary, the Lagrangian function combines the utility function with the constraint equation, incorporating the Lagrange multiplier to account for the constraint while maximizing the utility. By taking the partial derivatives of the Lagrangian function with respect to x, y, and lambda, and setting them to 0, we can find the optimal values of x and y that maximize the utility while satisfying the income constraint. Let's break down the process of taking partial derivatives of the Lagrangian function, and setting them to 0 to find the optimal values of x and y. Lagrangian function, L equals U plus lambda, C, R10M. U is the objective function, aggregate utility U equals x caret 0.5 plus y caret 0.5. Lambda is the Lagrange multiplier. C is the constraint equation, C equals x plus y, R10M. To find the optimal values of x and y that maximize the utility while satisfying the income constraint, we use the method of Lagrange multipliers. Take the partial derivatives of the Lagrangian function with respect to x, y, and lambda. Lx equals ux plus lambda, cx, ly equals uy plus lambda, cy, ls equals c, R10M. Set the partial derivatives equal to 0 and solve the resulting system of equations simultaneously. Else x equals 0, else y equals 0, else equals 0. By setting the partial derivatives to 0, we are looking for the critical points or stationary points of the Lagrangian function. Solve the system of equations to find the values of x, y, and lambda that satisfy the conditions. The solutions obtained will correspond to the optimal values of x and y that maximize the utility function u, while satisfying the income constraint. By finding the values of x and y that satisfy the stationary conditions, we ensure that we have found a local maximum or minimum of the Lagrangian function. In this case, we are looking for the maximum since we want to maximize the utility function. It's important to note that the process of solving the system of equations can be algebraically intensive, but it provides a systematic way to find the optimal values of x and y that satisfy the given constraints and maximize the utility.